What we want to do now is look at how data varies. And so we'll call this measures of variation. And this is important because, well, we'll start with an example that shows the importance of this. But let's define what we're going to talk about here. We're going to look for a range of the data set. We're going to find a measure called the variance and its relation to the standard deviation, both of a population and of a sample. There are slightly different rules for a population and a sample, and this is why we're using Greek for population and Roman letters, the Roman alphabet for samples, so that we can distinguish because of some of these small variations that happen with certain equations. We're going to define an empirical rule that gives a relative, quick, and easy way to talk about standard deviations. We're going to look at Chebyshev's theorem, which helps us with data that isn't symmetrical. And then we'll go back to our frequency distribution tables, and we'll learn how to approximate a standard deviation when we don't have every data value, but we have the midpoints and the frequencies. And then we'll develop the concept of a coefficient of variation that we can use for comparing two different data sets. And so one of the first things we do is we're going to talk about the range of the data, which is the maximum entry minus the minimum entry of the data. And it talks about on the number line how far the data is expanded. So let's look at these two corporations and their salaries in thousands of dollars. And what we're going to do is we're going to find the range. So in the range, we want to take the smallest data value, which is 47, and subtract it from the largest data value, which is 57. And that gives us a range of 10. While in corporation B, we're going to take the smallest data value, 33, and subtract it from the largest data value, 68, which gives us 35. But let's see why this is important. So I'm going to come over to Excel where I have these two corporations' data in place. And we're going to do what we did before. We're going to figure out the count, the mean, the median, and the mode. Then we'll calculate the range. So the number of pieces of data in the data set is equal to the count. So I take the equal sign for the formula to begin. I type in count, and that's from B2 to B11. So there's 10 pieces of data. The mean is the average over the same data set, B2 to B11. The median is median over the same data set, B2 to B11. The mode is mode from B2 to B11. And I'm going to calculate the range. So the range is the max minus the min. Well, luckily Excel has functions for us. It doesn't have a range function, but it does have a max function. So if I find the max from B2 to B11, and I subtract from it the min of B2 to B11, so I take the max minus the min, and I get 10. What we want to do is we want to compare these values to corporation B. So we're going to do the same thing. We're going to look for the number or count of objects, or the count of data entries, the mean, the median, the mode, and the range. So again, I'm going to use the same commands, count F2 to F11. I'm going to use average F2 to F11. I'm going to use the median from F2 to F11. I'm going to use the mode command from F2 to F11. And again, I'm going to take the max from F2 to F11 minus the min from F2 to F11. And notice that the data has the same mean, median, and mode. So the central tendency of both sets of data is the same, but Corporation A's salary only covers 10 values, $10,000 across the number line. While salary from Corporation B only spreads over $35,000 on the number line. And so this is not spread as much as this data. And let's look at what this looks like. So if we look at these graphed in a histogram along the same number axes, Corporation A, and all these bins are set to be the same width. So instead of depicting the number of classes, we force the bins to be the same width so we can compare the two. So Corporation B ends up with more bins, while Corporation A has 3 visible bins. And Corporation A, all of the data is tight near the center, while Corporation B, the data is spread out. And so what we want to do is we want to find a way to give a good measure of that spread. And the range is a good first measure. But we can talk a little bit more about it and get into a little more detail on it. So let's come here and we're going to talk about the idea of a deviation. And the deviation is how much the data value is away from the mean. And so for a population, we would say that's the data value x minus the mean. But we're going to use mu to represent a population mean. For a sample, it's the data value x minus x bar, the mean, but we're going to use x bar to represent a sample data set. So I'm going to come back to Excel and I'm going to focus on Corporation A. And we're going to make a table column to calculate the deviations. So I'm going to come over and I already plopped them into a separate sheet. And so I have all of my salaries in Corporation A, and I'm going to need to find the mean. So I'm going to come down here and make an entry for the mean. Again, the mean is the average of the data, so that's from B2 to B11. And when I hit tab, it puts that through. So the mean is 51.5. Well, I can make a calculation using this. So I can say Excel B2 minus. Now, when I pull down the box to create calculations, Excel adds 1 to each row in the calculation so that it generates new formulas. But because the mean isn't moving, I need to anchor that value. So I'm going to put $, B, $13. And we can think of the dollars as anchors. They keep them from shifting. And so the deviation of the first data value from the mean is negative 0.5. And I'm going to drag my box down here. And I get the deviation of each data value. And so one of the things I could do is let's add up the deviation. And so I'm going to, right, how much does this data set deviate overall? So I'm going to come down here and I'm going to use the sum command to add up C2 to C11. And notice we get 0 for the sum of the deviations. And the reason for this is if the data is symmetric, the mean is in the center, larger data values will have an equal lower data value. And so when I subtract them, their deviations cancel out. Or when I add them, their deviation cancels out because one is negative and one is positive. For example, this 0.5 here gets canceled by this 0.5. And these 3.5 and this 2.5 leaves a 1, which cancels out those 0.5s. There's 5.5 and the negative 4.5 leaves, and so there's a canceling on both sides. And this is common with symmetric data, that the deviation goes to 0 when you sum across it. And so if we want a measure of how the data is deviating, we have to do a little trick here. So what I'm going to do is I'm going to take a second here and go back to my blackboard. And when we talk about the distance between things, especially points that are given xy values, we can think of them as existing on the right triangle. And if this was x1 and y1, and this was x2 and y2, if I go from this point up to this point, that was a change in y of y2 minus y1. And if I go from this point to this point, that was a change in x of x2 minus x1. And if we ever wanted to find the distance, we used Pythagoras' theorem. A squared plus b squared equals c squared. Well, from a distance standpoint, it is the distance squared is equal to that change in my x's squared plus the change in my y squared. And so the distance of x2 minus x1 squared there we go, and y2 minus y1 squared, we take the square root. A similar thing is going to happen with our deviations. So the deviation for a pop is equal to x minus mu. And if I want to find the distance of this, what I can do is I can square it. And so if this deviation was negative, a negative number squared is positive, and this deviation was positive, a positive number squared is positive. And so this gives me a distance squared. And so if I take the square root of it, I'll always get a positive number. So that sets us up for something that's called the standard deviation. So let's come back here and look at the standard deviation and the variance as a formula. Now the variance is related to the standard deviation. For a population, it's going to get the Greek letter sigma lowercase. Again, mathematicians being lazy, right? We used uppercase sigma to represent a sum. We're going to use lowercase sigma to represent standard deviation. And the variance is the square of it. It's dealing without the square root. If we look at it, it's asking for the sum of all the deviations squared, and then it's dividing it by the number of entries in the population. It then takes the square root of it, and we can think about the standard deviation of being not exactly, but close to what we're going to call the average distance the data is from the mean. The standard deviation measures the variation about the mean, and because the standard deviation takes the square root, it ends up having the same units as whatever the data was measured in. It's always a positive number, and if the standard deviation is 0, there's no variation at all, which means all pieces, if nothing varies, every piece of data has the same value. If the data is spread further and further from the mean, or if it's more spread out, the standard deviation is large. So the standard deviation is 0, there's no spread, the values are the same. The larger the standard deviation gets, the greater it gets spread out. So what we're going to do here is we're going to look at a standard deviation calculation. We're kind of set it up by hand, and then we're going to go into Excel, and we'll do what we did by hand in Excel. And then we're going to look at the commands that Excel has to calculate standard deviation for us. Now, and variance. These are so often used that there are many commands for it, but we're going to have to pay attention to the difference between the population and a sample. It's a very important difference. We're going to start with finding the population variance and standard deviation. And there's 6 steps to it. You'll see the steps in the slide in the textbook, and the formulas are in the Appendix D, but we're going to show how to do this, and really we're going to make a column of information for it. So you want to start by finding the mean, then you want to find the deviation of each entry, then you're going to square the deviation, and then we're going to sum up all of the deviations. And then once you have the sum, we're going to divide it by the number of entries in the data, and that will be the variance. Then we're going to take the square root, and that'll be the standard deviation. We'll do one of these by hand, and then we'll jump over to Excel. We're going to use the Corporation A data that we've been using. So if we look really quick here, this is the data we're going to do. But I'm going to show you how to set up the table, and then we're going to mimic the table we do by hand in Excel. So let me pop over to my Blackboard here. Let me erase this. And let me make a table here. And there were 10 data entries, so I'm going to need 10 little boxes here. This is when I probably should get a default template that has grids and lines for me. 7, 8, put one up above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll have room for additions. So I'll start by listing all the X values that we had from Corporation A. Again, you can page back for it. I'm just going to pull it from 51, 48, 49. Let me call this a date. 51, 48, 49. 55, 57, 51. 54, 51. 54, 51. 47, 52. And so the first step is to find the mean of the data. So we would add up all the x's, and then we would divide that by 10 since there were 10 pieces of data. And since we are, and remember, we're saying this is a population, so we're going to say the mean is 51.5. Remember, we calculated this before, right? We come back over here and we look in Excel. We had calculated the mean as 51.5. Now, what we're going to do then is we're going to take the data value and we're going to subtract the mean from it. And notice how we're keeping all this information in columns. So 51 minus 51.5 is negative 0.5. 48 minus 51 is negative 3.5. 49 minus 51 is negative 2.5. 55 minus 51 is 4. Or I'm sorry, 49 minus 51.5 is negative 2.5. And 55 minus 51.5 is 3.5. 57 minus 51.5 is 5.5. 51 we already did, so I'll write that back down here. And 54 minus 51.5 is negative 2.5, or positive 2.5. And we already did 51. And 47 minus 51.5 is negative 4.5. And 52 minus 51.5 is positive 0.5. So we've made a column of all the deviations. So I'll come back here to our steps. Where did it go? I just lost. There we go. There, it's back. Sorry about that. So we found the mean and we found the deviation for each entry. So the next thing we need to do is we need to square the deviations. So what we do is we make a column for the squares. Notice how we're using columns to organize each of the steps. Because there's sums involved, it's easier to do things in columns. And so we're going to square each of these numbers. So if we square each of these numbers, running to my calculator here. I'm typing in negative 0.5 squared, and I get 0.25. So let me, get the right thing here. So remember, squaring a negative number becomes positive. So we get 0.25. Negative 3.5 squared is 12.25. Negative 2.5 squared is 6.25. Three 3.5 squared is 12.25. 5.5 squared is 30.25. We already did this one, right? Up here, 0.25. We already did this one because a positive times a positive gives me the same thing. And 4.5 squared is 20.25. And this is 0.25. Now our next job is to sum down this column, or to add up all of these. And so if we go look at our steps, add all of the squared standard or the squared deviations. So this sigma says do a sum, and we're doing a sum of the deviations squared. So if we come back and look at our column here, that sigma asking for a sum says add up this column. So we're going to add up the deviations squared. And so it's the total of this column. So running that through in the calculator, 0.25 plus 12.25 plus 6.25 plus 12.25 gives me a sum of 88.5. So we found the mean, we found each individual deviation, we squared each individual deviation, and we added them all up. To find the variance then, we divide that by how many pieces of data are in our data set. And in this case, we had 10 pieces of data. So I come back here. Let me clean a little bit of the screen off here. Hold on 2 seconds. Clear some space here. I need a better eraser than this. There we go. Looks like an eraser even, doesn't it? Let's see here. This really does feel like me being at the blackboard in front of class on Tuesdays and Thursdays. All right, and let me get back to my smaller brush. Nope. All right, and so the variance, which is sigma squared, was equal to the sum of the deviations squared divided by the total number of data sets, and our n was 10 here. And so we calculated by summing up this column the sum of the deviations. So this is 88.5 divided by 10, or 8.85. And so we have our variance. This is the variance. Well, if I want to turn the variance to a standard deviation, the standard deviation is the square root of the variance. And so we're looking for the square root of 8.85. And so, again, you hear me clicking in the back as I run to my calculator. Let's see here, 8.85. Take the square root. and 2.974. And so our standard deviation sorry, I gotta control the sensitivity on this. Our standard deviation is 2.974. Now again, if standard deviation is 0, all the data is in one place. And so there is no variation, no deviation. And if as our standard deviation increases, the data spreads out more. Well, this is a pain to calculate by hand. I've known a few instructors in the past that would give students, data sets and want them to do this by hand. I think understanding how it's built and recognizing when we square something, I think one of my keys is that the sum of the deviations itself is almost always 0, and so that we have to square it to turn it to all positive numbers, and that's why the square root appears back here. If we didn't take the square root, the standard deviation wouldn't be in the same measurement. But let's look at how we can do this in Excel. Since we already started by calculating the deviations earlier, we can use columns to take care of all the information for us. And it makes it easy to calculate. So where's my Excel? We'll come here. We already have population A in our Excel sheet. And so we calculated the deviation, so we're going to need to now square. And to square something, again, I'm going to take cell C2, which is my deviation, and I'm going to use the caret, which is shift 6, 2. And that mathematically will square it. So C2 caret 2 squares it, and I get my 0.25. Well, again, because I don't want to type that in over and over again, I drag down my box. And there are all my deviations squared. But we wanted the sum of the square deviations, right, the SSDs. And so we'll go back to our trusty sum command, equals sum. And we go from D2 to D11. And we get the 88.5. And so now to find the variance, I'm going to come up here just for visibility. I'm going to say the variance. Well, our variance was this sum divided by the number of entries. So I'm going to go, where's my sum at? It's at D14, but I don't want it to move, so I'm going to put $1 on it. Remember, if we don't want things to move, we anchor them in dollars. And we're going to divide it by the count of B2 to B11, the count of our data. And so our variance is 8.85. Our standard deviation, which I'll abbreviate STDEV, well, that's going to be the square root, so SQRT for square root, of the variance, which was G2. And there's the 2.97489. Well, that's a lot of work. And there's a couple questions in Pearson that will ask you to build the columns and add them together. But what's nice is that Excel does some of the work for us. So if I go equal STDEV, and I can put in B2 to B11, and that'll give me a standard deviation. Oh, but it's not the same. Let's look at this more closely. If I type in STDEV, notice I have some different options. I have a .p, which is saying, hey, you're doing it on a population, and a .s if you're doing it on a sample. If I don't put the dot in at all and just do STDEV, it will assume I'm doing a sample. But we said this was a population. These were all 10. So we're going to use the .p And now we're going to do B2 to 11. And we get the same result. Please be very, very careful. In a couple slides, I'll show you the difference between the calculation between a sample and a population. But when you're using standard deviations, make sure that if it's a population, use the population function, either on your calculator or in Excel. And when it's a sample, use the sample function, either on your calculator or in Excel. So let's see what's going on here. Your textbook rounded this up to 3. So what happens for a sample standard deviation is that we get an n-1 on the bottom. And that n-1 changes the value. And when I took graduate level statistics, we kind of proved why this is different. But I'm going to try to sum it up is when I have a population, I have every piece of data. And so I have the ability to divide that across and it's averaging accurately. But when I have a sample, I don't have every piece of data. There could be another piece of data out there. And that piece of data might change the inference of things. And so when I'm looking at each piece of data, I kind of have to average them together and wholly. And what ends up happening is this means I could always get another piece of data. And again, the best way of saying it is when you have the population, you have everything. There's no more to get. But when you have the sample, there are other pieces of data out there that you don't have. And so you leave room for them with this n-1. It's the best way I can describe where this comes from. And I mean, it's a little more convoluted than that, but that's how I remember the difference is the population has everything. I don't need to change the n. The sample doesn't have everything, so I leave room for other pieces of data. And the process of finding this is exactly the same. The only thing that changes is the division. So we find the mean of the data set. Again, please note, because we're talking about populations now, we have a lowercase n, and our mean is going to be x bar. We find the deviation of each entry, which is the same. And then we square the deviation, and then we take the sum of it. The step that changes is when we go to get the sample variance, we divide by n-1 instead of n, which means the sample deviation will be the square root of the sum of the deviations divided by n-1. All right, I'm going to stop the video here. I'm going to do a small video of an example of finding a sample deviation using Excel. Actually, I'll do the example now, and then I'll stop the video. So we saw how we could do a table, and we also saw that Excel has a command in it. I'm going to create another sheet here for this data set. Let me make this large enough for you to see. And I'm going to use the example. I haven't moved it across here yet. I'm going to use the example here. So we have high school football players who have sustained concussions. Researchers placed the players in 2 groups. Players that recovered from their concussion in 14 days or less were placed in group 1. Those who took more than 14 days were placed in group 2. The recovery time for group 1 are listed below. Find the sample variance and standard deviation of the recovery time. So this is going to be the data I'm going to enter into Excel. So let's come over here to Excel. I have a new set of places for the data. Let me get the size of that right. And so this is recovery in days. And let's list our data across 8, 10, 4, 6, 7. 8, 10, oops, sorry, I didn't mean to shut the window on you guys there. 8, 10, 4, 6, 7, 7, 9, 10, 7. So I'm entering all my data in. 6, 5, 11. I'm going to do what I've done with every piece of data before, and I'm going to do it over here. So in all of these data sets, I'm going to find my count. Again, we will be using larger data sets here, and the count might not always be easy to see quickly. So I'm just making a habit of using my sum command, my average command, which I know, which is B2 to B13, my median, my mode, and let's see here. I want to actually use the multi-mode. So I'm going to select, let's see, we'll hope it has 2. So I've selected 2 cells for the output. I'm going to use equal mode dash mult. I'm going to go B2 to B13, and then I'm going to go Control Shift Enter. And it looks like 7 is my only mode, because 7 is the largest number there. All right, so I'll come in. And we'll delete that cell. Oops, did this the last time. Boom, boom. We'll delete both of them. And I will just do it on 1. So I had 7 and 6, but 7 is definitely more populous than 6. And so we'll have the mode there. So we have the mean, median, the mode. Let's look at the range. So that's the max. Right? We're using our functions. The max, B2 minus B or 2B13 minus the min, B2 to B13. And so the range of the data is 7. So we have our mean, median, and mode, the range of our data. And now we want to find the variance and the standard deviation. So I'm going to write the standard deviation first, and it is a sample. So let's do the variance first. So we're going to equal var dot s, because it's a sample, and we're going to do B2 to B13. And so our variance is 4.636 repeating. Our standard deviation is going to equal standard deviation dot s, because it's a sample, of B2 to B13. And so we can calculate our variance and our standard deviation using our Excel commands directly. And I think this is a good place to pause this video and separate it into another video.